in a few years, Voyager 1 will go silent. No final message, no goodbye, just nothing. But here is what nobody talks about. Death for Voyager 1 is not the end of the journey. It is just the beginning of the longest one. How far does a dead spacecraft travel through interstellar space? If you love the kind of content that makes the universe feel both terrifying and beautiful, make sure to give this video a like. Now let's get started. Right now, as you watch this, Voyager 1 is roughly 25.5 billion kilometers away from Earth. That number is so large it barely registers, so let's break it down in a way that actually lands. You know how long it takes sunlight to reach us from the Sun? About 8 minutes. That is the distance we call 1 astronomical unit, the gap between Earth and our star. Voyager 1 is currently sitting at about 170 of those units away from the Sun, 170 times the Earth-Sun distance, and it is getting farther every single second. Here is another way to feel it. A signal traveling at the speed of light, the fastest anything in this universe can move, takes roughly 23 hours to reach the spacecraft from Earth right now. You send a message, you wait a full day, and it has only just arrived. Then you wait another day for the reply. A simple back-and-forth conversation with Voyager 1 takes nearly 2 full days. That is not science fiction. That is the reality of what deep space actually means. And that distance is only going to keep growing, because Voyager 1 is not slowing down in any way that matters. Out in the void between stars, there is virtually no air, no friction, nothing pushing back against it. The Sun's gravity is still technically pulling at it, but from this far out, that pull is barely a whisper. So the spacecraft just keeps gliding forward at roughly 17 kilometers every single second. That is about 61,000 kilometers per hour. In the time it takes you to read this sentence, Voyager 1 has already covered several hundred kilometers. Now, here is the question that is probably already forming in your mind, and it is exactly the right one. How did a machine built by human hands in the 1970s end up out there? And what is actually going to happen to it? The story begins on September 5th, 1977. That is when NASA launched Voyager 1 from Kennedy Space Center in Florida. To understand what a big deal that launch was, you have to understand the moment in history. It was just 8 years after the first moon landing. Personal computers did not exist yet. The smartphone was still decades away. And yet a team of engineers built something so well designed, so carefully thought through, that it is still working today. Nearly half a century later, the original mission was never meant to last this long. Voyager 1 was designed for a 5-year tour of the outer solar system. The plan was to swing past Jupiter and Saturn, study their moons and rings up close, and beam back data that no telescope on Earth could ever gather. And it delivered in spectacular fashion. In March of 1979, Voyager 1 made its closest approach to Jupiter, coming within about 349,000 kilometers of the giant planet. The images it returned were jaw-dropping. We got our first truly detailed look at the Great Red Spot, a storm larger than Earth that has been raging for hundreds of years. We saw the volcanic eruptions on Io, one of Jupiter's moons, the first active volcanoes ever spotted on another world beyond Earth. We discovered that Jupiter had a faint ring system that nobody had known about before. One flyby, one spacecraft, and it completely reshaped our understanding of the largest planet in our solar system. Then came Saturn. In November of 1980, Voyager 1 made its closest pass of the ringed planet. It studied the iconic rings in stunning detail, revealing a structure far more complex and beautiful than anyone had anticipated. Thousands of individual ringlets, braided patterns, strange gaps carved out by the gravity of nearby moons. It also made a targeted close approach to Titan, Saturn's largest moon, a world wrapped in a thick orange atmosphere that hid its surface from view. Scientists were fascinated by Titan because it might, in some ways, resemble early Earth, but that Saturn flyby did something else. It bent Voyager 1's path. The way a gravitational slingshot works is that the spacecraft steals a tiny bit of a planet's momentum, uses the planet's own gravity as a kind of cosmic catapult. That encounter with Saturn sent Voyager 1 rocketing up and out of the flat plane where all the planets orbit, up and away from the solar system, and from that moment there were no more planets to visit, no more adjustments to its course, just open space stretching out forever. Speaking of what it takes to travel through the deep dark between stars, if the idea of humans one day attempting that journey fascinates you, I actually made a video about exactly that. We explore how long a generation ship would survive in deep space. It's on the card above. It digs into what it would really take for a crew to make it across the void. Check it out after this one. The link is in the description and pinned on the comments. Now, here is where the story really starts to become something more than just engineering. After Saturn, Voyager 1 kept flying, and flying, and flying, for years, then decades. The team at NASA's Jet Propulsion Laboratory tracked it faithfully, watching its distance grow, monitoring its health, listening to its faint transmissions. Then, on August 25, 2012, 35 years after launch, something extraordinary happened. Instruments aboard the spacecraft detected a sudden, dramatic shift in the particles and magnetic fields surrounding it. The steady stream of charged particles blowing outward from our sun, what scientists call the solar wind, abruptly stopped. In its place, a different kind of plasma appeared, denser, coming from all directions rather than flowing outward from a single source. Voyager 1 had crossed the heliopause, the boundary where our sun's influence fades and true interstellar space begins. It became the first human-made object in history to enter the space between stars. Think about what that means. We sent something out of the bubble, out beyond everything the sun touches. The electromagnetic shield, our star, has been projecting across billions of kilometers. The cocoon it wraps around our entire solar system, Voyager 1 punched through it and came out the other side. No other spacecraft has ever done that before. Voyager 2 followed in November of 2018, becoming the second, but Voyager 1 was the first, and it got there by crossing roughly 121 astronomical units of space, more than 4 times the distance to Pluto. Now you might be thinking, okay, so it left the solar system? Done. Mission complete. But here is where it gets genuinely fascinating and a little heartbreaking, because the story is not over. In fact, some of the most remarkable chapters are still being written, and Voyager 1's days are numbered in a way that makes all of this feel even more profound. Here is what is quietly ticking away inside that spacecraft right now, and what it tells us about exactly how much time is left. Voyager 1 runs on something called radioisotope thermoelectric generators. 3 of them, instead of solar panels, which would be completely useless this far from the sun. These devices use the heat produced by the natural radioactive decay of plutonium-238 to generate electricity. At the moment of launch, those generators were putting out roughly 470 watts, about enough to power a couple of bright light bulbs, but plutonium does not decay forever. Every year, those generators lose a little more output, roughly 4 watts annually. By now, nearly 50 years on, the power budget has dropped to something in the range of 249 watts, and it keeps falling. Every year, the engineering team at JPL has to make harder and harder choices about what gets to stay on and what gets shut down, because there simply is not enough electricity to run everything. The cameras went first, back in 1990. That farewell moment came on February 14th of that year, when mission controllers asked Voyager 1 to turn its camera back toward home one last time. From 6 billion kilometers away, it snapped a portrait of our solar system, a mosaic of frames showing the planets as tiny specks of light against the vast darkness. Earth appeared as a pale blue dot, less than a single pixel across, suspended in a sunbeam. Astronomer Carl Sagan described that image in words that still, decades later, send a chill through anyone who truly sits with them. He said, "Look again at that dot. That's here, that's home, that's us." Then the cameras were switched off for good to save what little power remained. Since then, instrument after instrument has been powered down. The ultraviolet spectrometer went dark in 2016. The cosmic ray subsystem, the very tool that helped confirm Voyager 1's entry into interstellar space, was switched off on February 25, 2025, purely to save electricity. The low-energy charged particle detector followed on April 17, 2026. As of right now, only 2 science instruments remain active: the magnetometer, measuring the magnetic field of interstellar space, and the plasma wave subsystem, listening for vibrations in the thin sea of charged particles that fills the void between stars. 2 instruments, out of the 10 it launched with. And the clock is still ticking. But before we talk about when the lights finally go out, there is something else you need to know. Something that happened just a couple of years ago that genuinely shocked the scientific community and reminded the world that Voyager 1 still has surprises left to give. Because in late 2023, the spacecraft started doing something deeply unsettling. It started sending gibberish, "Stay right here," because what happened next and what NASA did to fix it from 24 billion kilometers away is one of the most extraordinary feats of engineering in the history of space exploration, and it changed everything about how long we think Voyager 1 might actually survive. So let's pick up exactly where we left off, because what happened to Voyager 1 in late 2023 is the kind of story that sounds like it belongs in a movie, except it is completely real, and the stakes were as high as they get. It started quietly. In October of 2023, the engineering team at NASA's Jet Propulsion Laboratory noticed something strange coming through in Voyager 1's transmissions. The spacecraft was still communicating, the signal was still arriving, but the data being sent back from the flight data system, the onboard computer responsible for packaging scientific and engineering information before beaming it to Earth, had turned into nonsense. A repeating pattern of ones and zeros that carried no meaningful information whatsoever, just noise. The team could still tell the spacecraft was alive. Its heartbeat was there, but it was like getting a phone call from someone and hearing nothing but static on the other end. You know they are there. You just cannot understand a single word they are saying. Now, pause for a moment and really feel the weight of this situation. The engineers trying to diagnose this problem are sitting at desks in Pasadena, California. The patient, if you want to call it that, is a spacecraft roughly 24 billion kilometers away. Every command they send takes approximately 22.5 hours to arrive. Every response takes the same amount of time to come back. A single diagnostic question and its answer takes nearly 2 full days. In medicine, when something goes wrong, you run tests in real time, you adjust, you try again immediately. Out there, every single attempt costs 45 hours of waiting. You do not get to be impatient. You do not get to rush. You have to be absolutely certain before you do anything, because one wrong command sent carelessly could silence the spacecraft forever. The team spent weeks just trying to understand the shape of the problem. They sent commands asking the flight data system to report on its own status. The replies came back garbled. They tried different approaches, different diagnostic routines, all while double and triple checking every instruction before it left the antenna. Then, in December of 2023, after months of painstaking work, they had a breakthrough. one of the three onboard computers, specifically the Flight Data System computer, had a corrupted memory chip, not a software glitch, not a programming error, a physical chip inside the hardware that had developed a fault. Roughly 3% of the Flight Data System's memory had simply stopped working correctly. And because all the code responsible for packaging and transmitting science and engineering data was stored in that section of memory, the whole output had collapsed into meaningless patterns. Here is what made this genuinely terrifying. You cannot send a replacement chip to a spacecraft 24 billion kilometers away. You can plug in a USB drive with a fresh copy of the software. Whatever fix existed had to be done remotely, using the original hardware, working around a broken piece of memory that had been running continuously since 1977. The solution the team came up with was, in the most literal sense, extraordinary. Rather than trying to fix the damaged memory, which was impossible, they decided to move the affected code. Piece by piece, they would relocate the corrupted sections into other parts of the computer's available memory, adjusting the code so that all the different sections could still communicate with each other, even though they were no longer stored in one continuous block. Imagine taking apart a book, chapter by chapter, storing each chapter in a different room of a massive building, and then rewriting all the page numbers and references so the whole thing still reads correctly when you put it back together from 24 billion kilometers away. With a 45-hour round-trip delay on every single instruction, it took months. The first relocated section of code was successfully transmitted and tested in April of 2024. The spacecraft began returning usable engineering data again, real, coherent information about its own health and systems. For the first time in roughly 5 months, the team erupted. People who had dedicated years, in some cases their entire careers, to this mission were in tears, because they had done what most people outside that building genuinely thought might be impossible. They had reached across a distance that dwarfs all human experience, found a broken piece of a 47-year-old machine and fixed it. By the summer of 2024, all 5 of Voyager 1's remaining operating science instruments were back online and returning data. The magnetometer, the plasma wave subsystem, all of it working again. The mission, which many had quietly feared might be over, had been given more time. And here is why that matters beyond just the engineering triumph. Because the data Voyager 1 is still gathering, right now, today, is not redundant. It is not repeating things we already know. It is genuinely irreplaceable science from a place no other instrument has ever been. Think about where the spacecraft actually is. It is drifting through the local interstellar medium, the thin, diffuse ocean of gas, dust, plasma, and magnetic fields that fills the space between star systems in our region of the Milky Way. This is not empty space in the way you might imagine emptiness. It is a living environment, in a cosmic sense, threaded with ancient magnetic field lines, peppered with charged particles thrown out by long-dead stars, vibrating with low-frequency waves that travel enormous distances. And Voyager 1 is the only instrument we have ever placed inside it. Everything we knew about the interstellar medium before Voyager 1 got there was based on remote observation, like trying to understand the chemistry of the ocean by looking at it from a satellite. Now we have something actually swimming in it, tasting it, measuring it directly, and what it has found has already surprised scientists in multiple ways. For example, the density of the plasma in the local interstellar medium has turned out to be significantly higher than most models predicted. In 2021, scientists analyzing data from Voyager 1 detected persistent plasma oscillations, essentially the interstellar medium humming at a consistent frequency. a faint, continuous wave signal that had not been expected. Some researchers described it as a kind of hum, a quiet drone that fills the space between stars. The universe, it seems, is not silent out there. It has a voice, it is just very, very quiet. The magnetic field data has also yielded surprises. The boundary region between the solar wind's influence and true interstellar space turned out to be more complex and dynamic than anyone anticipated. There are layers, gradients, unexpected turbulence. The heliopause is not a clean wall, it is more like a chaotic shoreline where two different oceans of plasma push against each other in constantly shifting ways. Voyager 1 crossed it once, but its readings since then have shown that even in interstellar space, the sun's influence does not simply vanish. Its presence can still be felt, subtly, for a surprisingly long distance beyond the boundary. All of this data feeds directly into models of how our solar system interacts with the rest of the galaxy. It informs our understanding of how the heliosphere, the sun's enormous magnetic bubble, protects Earth and the other planets from cosmic radiation. Because that is what the heliosphere actually does. It acts as a shield. The charged particles hurled across the galaxy by supernova explosions and other violent events, cosmic rays, some of them carrying energies millions of times greater than anything our particle accelerators can produce. Those particles are deflected and slowed by the heliosphere before they reach us. Without it, the radiation environment in our solar system would be dramatically different. Life on Earth might not have been possible at all. Voyager 1's measurements help us understand exactly how effective that shield is, where it weakens, how it responds to changes in the sun's own activity cycle. That is not just interesting astronomy, that is fundamental knowledge about why life exists on this planet. Now, let us zoom out even further, because the journey Voyager 1 is on puts something into perspective that most people never truly stop to consider, even at 17 kilometers per second, even after 50 years of continuous flight. Voyager 1 has barely scratched the surface of what lies between us and the next star system. Our nearest stellar neighbor is Proxima Centauri, a small red dwarf star about 4.24 light-years away. A light-year is the distance light travels in one full year, roughly 9.5 trillion kilometers. Proxima Centauri is approximately 40 trillion kilometers from our Sun. Voyager 1 is currently about 25.5 billion kilometers away. That means it has covered, after 50 years, roughly 0.06% of the distance to the nearest star. If you scaled the distance to Proxima Centauri down to the length of a football pitch, 100 meters, then Voyager 1 has traveled about 6 centimeters. 6 centimeters out of 100 meters. In 50 years, this is not a criticism of the spacecraft or the mission. This is simply what the universe is. It is enormous in ways that our brains are genuinely not equipped to process. The distances between stars are not just large, they are an entirely different category of large, and Voyager 1, for all its incredible achievement, has given us only the tiniest possible first step into that immensity. At its current speed, it would take Voyager 1 roughly 73,000 years to travel the distance to Proxima Centauri, assuming it were even headed in that direction, which it is not. It is actually moving toward a region of the constellation Ophiuchus, and in about 40,000 years, it will pass within about 1.6 light-years of a star called Gliese 966, also known as ASA plus 79 3088. Not a close flyby by any stretch, but a flyby nonetheless in the deep time sense of the word. And this is where the question at the heart of this video becomes truly poignant, because Voyager 1 will not be alive, scientifically speaking, for anywhere near those 73,000 years. Its instruments are already shutting down one by one, victims of the relentless mathematics of radioactive decay. Within the next few years, the last remaining science instruments will go dark, the transmitter will fall silent, and the spacecraft will become, to all intents and purposes, a ghost. But here is the thing, and stay with me here, because this is where the story gets genuinely profound. The death of Voyager 1 as a scientific instrument is not the end of the story, not even close. What happens after the signal dies is something far more ancient, far more elemental, and in some ways far more beautiful than anything that came before it. And it has everything to do with what it means to send something out into the universe, and what the universe does with it afterward. But to understand that fully, we need to talk about something most people have never considered: what is actually waiting for Voyager 1 in the space it is about to enter. Not the emptiness, not the silence, something stranger, something that scientists are only just beginning to map. Most people think of the solar system as ending somewhere around Pluto, maybe a little beyond. You picture the sun at the center, the 8 planets arranged in their neat orbital lanes, and then nothing, just open space stretching out to the stars. But that picture is incomplete in a way that genuinely changes how you understand where we are in the universe, because beyond the planets, beyond the Kuiper Belt where Pluto lives alongside thousands of other icy bodies, there is something else, something vast, something so enormous that it makes the entire planetary region of our solar system look like a small warm room inside an incomprehensibly large building. It is called the Oort cloud, and Voyager 1 is heading straight into it. The Oort cloud is not a place you can point a telescope at and see directly. We have never actually observed it. What we know about it comes from inference, from the behavior of long-period comets, those icy wanderers that occasionally swing in from the outer darkness, streak through the inner solar system in a brief blaze of light and sublimating gas, and then arc back out into the void on orbital paths that take thousands or even millions of years to complete. When astronomers trace those paths backward, they all seem to originate from a vast spherical shell surrounding the Sun at enormous distances. That shell is the Oort cloud. The inner edge of the Oort cloud is thought to begin somewhere between 2,000 and 5,000 astronomical units from the Sun. Remember, Voyager 1 is currently at about 170 astronomical units, so it has not even come close to entering the Oort cloud yet. The outer edge of the Oort cloud is estimated to extend anywhere from 10,000 to 100,000 astronomical units from the Sun, and possibly even further. At its outermost reaches, the Oort cloud might extend nearly halfway to Proxima Centauri. Let that land for a moment. The gravitational reach of our Sun, the halo of material it holds in its embrace, stretches nearly halfway to the next star. Our solar system is not a small neighborhood, it is a continent, and the planets, the place where all of human history has unfolded, all the wars and empires and art and science and love, that is just the warm inner courtyard. Now, the Oort cloud is thought to contain an almost incomprehensible number of icy objects. Estimates range from hundreds of billions to perhaps several trillion individual bodies, remnants from the formation of the solar system, chunks of ice and rock and organic material that were flung outward by the gravitational interactions of the giant planets billions of years ago. Most of them are small, many are the size of a city. Some are substantially larger, and they drift in an almost perfect silence, so far from the Sun that its light is barely brighter than any other star in the sky from their surface. These are the seeds of future comets. Every now and then, a passing star or the gentle gravitational tug of the Milky Way galaxy itself nudges one of these objects, disturbs its ancient orbit, and sends it on the long, slow fall inward toward the Sun. That journey can take millions of years, and when it finally arrives in the inner solar system, it blazes briefly, a visitor from deep time, carrying frozen material that has barely changed since the solar system was born 4.5 billion years ago. Scientists study comets partly for exactly this reason. They are time capsules. The materials locked inside them preserve a chemical record of conditions in the early solar system, the raw ingredients that eventually gave rise to planets and oceans and life. Some researchers have even suggested that comets may have played a role in delivering organic molecules to early Earth. Perhaps the very building blocks of the chemistry that eventually became you were carried here, billions of years ago on the back of one of these icy wanderers from the outer darkness. You are, in a very real and scientifically grounded sense, made of the same material that Voyager 1 is about to drift through for the next several tens of thousands of years. At its current velocity, Voyager 1 will begin entering the inner Oort cloud in roughly 300 years. It will spend, and this is not a typo, approximately 30,000 years traversing it before emerging on the other side. 30,000 years. At the time Voyager 1 entered the Oort cloud, our ancestors were painting caves in Europe and hunting mammoths across the Ice Age steppes of Asia. It will spend a span of time equal to all of recorded human history many times over just passing through this one region of our solar system's outer suburbs. And during that entire journey, there will be no signal, no transmission, no heartbeat, because the scientific instruments will have been dead for tens of thousands of years by then. The power will have run out long before the spacecraft reaches the inner edge of the cloud. Voyager 1 will be dark and silent, a metal artifact drifting through one of the most remote and ancient regions of our cosmic neighborhood, completely unknown to whatever civilization, if any, might exist on Earth at that point. The thought experiment almost breaks the brain. What will the world look like when Voyager 1 finally clears the Oort cloud? Will there be anyone left who knows it is out there? Will the concept of NASA even be remembered? Will humanity have spread to other planets, found a way to survive the deep future, or will we be long gone? Another brief flicker of complexity in a universe that was here long before us and will be here long after. There is something important to sit with here, and it connects back to the data Voyager 1 is sending right now. While it still can, the spacecraft is currently measuring the properties of the local interstellar medium, as we talked about in the last part. But that data is doing something beyond just satisfying scientific curiosity. It is helping us build a picture of the environment our solar system actually lives in. And that picture has direct consequences for some of the biggest questions in astronomy. One of those questions is, how typical is our solar system? How typical is the bubble our sun creates, the heliosphere, compared to the bubbles created by other stars? Because every star that has a stellar wind creates its own version of a heliosphere. Every star pushes back against the surrounding interstellar medium in its own way, shaped by its own wind strength, its own magnetic field, the local properties of the space it moves through. Voyager 1's measurements of where exactly the heliopause sits, how thick the transition region is, how the magnetic field behaves on both sides, all of that feeds into models that astronomers use to understand the astrospheres of other stars, stars that might have planets, planets that might have life. The radiation environment inside a stellar bubble is crucial to whether surface life on a planet is viable at all. A star with a weak heliosphere, or one moving through a particularly dense patch of interstellar medium, might expose its planets to significantly higher cosmic ray fluxes than Earth experiences. That matters enormously for the question of habitability. So the data coming from this one small spacecraft drifting through the dark barely 25 billion kilometers away has implications that stretch far beyond our own solar system. It touches on the question of whether life elsewhere in the galaxy is even possible, and under what conditions it might arise. Now here is something that does not get talked about nearly enough when people discuss Voyager 1, and it is something that cuts right to the heart of what this mission actually means in the deepest sense. On board Voyager 1 and its twin Voyager 2, there is a golden record, not metaphorically, a literal, physical, gold-plated copper disc 12 inches across, designed to last for at least 1 billion years in the environment of interstellar space. It was attached to the spacecraft before launch on the instructions of a committee chaired by Carl Sagan, who understood perhaps better than anyone that Voyager 1 was not just a scientific instrument. It was also a message in a bottle cast into the most enormous ocean imaginable. The record contains 115 images encoded in analog format, photographs of Earth, of humans, of our biology, our geography, our cities. It contains nearly 90 minutes of music from across human cultures: Bach, Beethoven, Chuck Berry, a Navajo night chant, gamelan music from Java, a Pygmy girl's initiation song, a Georgian chorus, a Japanese shakuhachi piece, Bulgarian folk songs, the sounds of Aboriginal Australians. It contains spoken greetings in 55 languages, from ancient Akkadian to modern Mandarin. It contains sounds of earth, wind, rain, surf, a mother's first words to her newborn child, the sounds of crickets and frogs, a train, a tractor, a rocket launch, a kiss. And it contains instructions etched into the record's cover in a kind of pictographic language, explaining how to build a device to play it back, explaining how to interpret the images, explaining where it came from, encoded in the universal language of physics and hadron spectroscopy. Whoever, or whatever, finds it, if anything ever does, will be able to reconstruct a portrait of what was alive on a small rocky planet orbiting an ordinary star in the outer arm of an average galaxy 4 or 5 billion years after that planet formed. The probability of anyone finding it is, to be honest, vanishingly small. The universe is almost entirely empty. The chance of Voyager 1 drifting within detection range of another civilization is effectively zero on any timescale that matters. Sagan knew this, everyone on that committee knew this, and they sent it anyway. Why? Why go to that effort for something so unlikely to succeed? Because the act of sending it meant something. Because the decision to include a Bulgarian folk song and the sound of a mother's voice and the mathematics of the hydrogen atom on a spacecraft flying out of our solar system was itself a statement about what we are. It said, we are curious, we are connected, we know we are small, and we reached out anyway. We looked up at the dark between the stars, and instead of fear, we felt wonder. Instead of silence, we tried to sing. That impulse, that irrepressible human need to communicate, to reach, to say we are here into a void that may never answer, is as much a part of the Voyager story as any flyby or any telemetry reading or any repaired memory chip, and it raises a question that might quietly follow you for a long time after you finish watching this video. Not a scientific question exactly, more of a philosophical one, more of a human one. If the universe is as vast and as silent as Voyager 1's journey suggests, if the nearest star is so far away that crossing to it would take longer than our entire civilization has existed, then what does it mean to reach out? What does it mean to explore? What does it mean to be alive in a cosmos this large, this old, this indifferent to our presence? And here is where the story of Voyager 1 stops being just about a spacecraft, because it starts to reflect something back at you about yourself, about what we value, about what we are willing to build and launch and chase across the dark, not because we know it will succeed, but because something in us cannot help it. The power aboard Voyager 1 is draining. Year by year, the generators give a little less. The list of instruments that have already gone dark keeps growing, and somewhere in the next few years, estimates converge on the mid-2030s as the likely window. The last instrument will go silent, the transmitter will lose power, and a machine built by human hands in the 1970s will become a ghost, dark and cold, carrying its golden record through the longest journey anything we have ever made will ever take. But before we get to that moment, and before we talk about what exactly those final years look like, and what Voyager 1 might still teach us before the lights go out, there is a chapter of this story that almost nobody talks about. A chapter involving the sun itself, a slow, enormous transformation happening right now on a timescale of billions of years that will eventually change the fate of everything in our solar system and cast a very different light on why Voyager 1's journey matters in the grand sweep of cosmic time. The sun is not going to burn forever, and what happens when it begins to die will reshape everything we think we know about what it means to be part of this solar system. If you are enjoying this journey, make sure to give this video a like and subscribe. Takes 1 second, but makes all the difference. Everything in this solar system exists because of one thing, one enormous, ancient, furiously burning sphere of plasma sitting at the center of it all, holding everything in its gravitational embrace, flooding space with light and heat and charged particles. The sun, 4.6 billion years old, 109 times wider than Earth, so massive that it accounts for 99.86% of all the mass in the entire solar system. The planets, the moons, the asteroids, the comets, the Oort cloud, Voyager 1 itself, all of it together is less than 1/4% of what the sun weighs. And right now, in this moment, the sun is in the most stable phase of its existence. Astronomers call it the main sequence. It is the long, quiet middle chapter of a star's life, where the gravitational pressure pushing inward and the nuclear fusion pushing outward are in near-perfect balance. Our sun has been on the main sequence for about 4.6 billion years. It will remain there for approximately another 5 billion years before things begin to change. But change they will, and when they do, the transformation will be so dramatic, so total, so absolute, that the solar system you know, the one Voyager 1 launched from, will essentially cease to exist. Here is what is coming in the deep future and why it matters to the story we are telling. Stars like our sun run on hydrogen, at the core, under pressures and temperatures so extreme that matter itself behaves in ways nothing on Earth ever does. Hydrogen nuclei are being slammed together and fused into helium. Every second, the sun converts approximately 600 million tons of hydrogen into helium through this process. Every second, the energy released by that conversion is what powers the sun, and by extension, what powers all life on Earth. The sunlight hitting your face right now is the result of nuclear fusion that happened at the core of the sun about 100,000 years ago, slowly working its way outward through layers of dense plasma before finally escaping as light. But hydrogen is not infinite. The sun is burning through its fuel supply. Slowly, over billions of years, the core is accumulating helium, a kind of ash left behind after the hydrogen fuel is spent. As the helium ash builds up and the hydrogen in the core runs low, the dynamics of the sun's interior will begin to shift. The balance that has held for billions of years will start to tip. Roughly 5 billion years from now, the hydrogen in the sun's core will be nearly exhausted. Without fusion at the core to push back, gravity will begin to win. The core will contract, heating up dramatically as it does. And that increase in temperature will ignite a shell of hydrogen surrounding the core, hydrogen that had not been hot enough to fuse before. Suddenly, the sun will have a new source of energy, and it will go to work with extraordinary violence. The outer layers of the sun will begin to expand. Slowly at first then, with increasing speed. The sun will brighten, it will swell. Over the course of hundreds of millions of years, it will grow into what astronomers call a red giant, an enormous, bloated, luminous sphere of plasma that will eventually expand to somewhere between 100 and 200 times its current size. By this point, Its outer atmosphere will have engulfed Mercury, then Venus. The fate of Earth is genuinely uncertain. Some models suggest our planet will be swallowed, others suggest it will survive just barely at the outer edge of the expanded atmosphere, scorched and airless and utterly unrecognizable. Either way, the surface of Earth will be molten long before that point. The oceans will have boiled away billions of years earlier as the gradually brightening sun made the inner solar system too hot to sustain liquid water. Now, why are we talking about this in a video about Voyager 1? Because this is the backdrop against which the entire human story plays out. This is the clock we are all living inside, whether we think about it or not. The sun that launched Voyager 1 in 1977, the sun that is powering the computers of the engineers who fixed its memory chip, the sun that is providing the energy for whoever is watching this video right now, that same sun is slowly, inexorably moving toward the end of its main sequence life. And everything that happens to humanity in the billions of years between now and then will happen in the shadow of that countdown. Voyager 1, drifting silently through the dark, is in a sense the only human-made object that has already started the process of escape. Not from gravity, the sun's gravitational influence extends far beyond where Voyager 1 will ever reach, but from the sun's light, from its warmth, from the particular electromagnetic embrace that makes the inner solar system habitable. Voyager 1 crossed into a region where the sun is just another star a long time ago. In that sense, it is a preview of a journey that the entire solar system is slowly, on a timescale of billions of years, beginning to take. And when the sun eventually exhausts its red giant phase, when it can no longer sustain even the shell burning that powers it during that phase, it will do something that is, in its own quiet way, almost beautiful. It will not explode. It is not massive enough for that. Stars several times more massive than our sun end their lives in supernova explosions, catastrophic detonations that can outshine entire galaxies for a brief period and leave behind neutron stars or black holes. Our sun will not go that way. Instead, it will gently shed its outer layers, a slow expanding bubble of gas and dust, pushed outward by the radiation from the contracting core, will drift out into the surrounding space over the course of tens of thousands of years. Astronomers call this a planetary nebula, a somewhat misleading name that has nothing to do with planets, inherited from early observers who thought these glowing shells looked vaguely like planet disks through their telescopes. The result is something genuinely spectacular, a glowing cloud of expelled stellar material, expanding outward, lit from within by the intensely hot remnant of the star's core, and that remnant, the dense Earth-sized, incredibly hot object left behind when the outer layers are gone, is called a white dwarf. It will be composed almost entirely of carbon and oxygen, the ash products of helium fusion that occurred during the red giant phase. It will be extraordinarily dense, a mass roughly equal to our current sun, compressed into a sphere about the size of Earth. A teaspoon of white dwarf material would weigh approximately 15 tons. It will glow with the stored heat of billions of years of nuclear burning, slowly radiating that energy away into space over billions more years, cooling from white to yellow to orange to red to eventually a cold dark object called a black dwarf. Though, to be precise, the universe is currently not old enough for any white dwarfs to have yet cooled all the way to that final dark state. The oldest white dwarfs we know of are still warm. The black dwarf era, if it ever comes, lies in a future so remote that it makes the current age of the universe look like a brief morning. Where will Voyager 1 be when the sun becomes a red giant 5 billion years from now? The mathematics here are almost meditative in their scale. At its current velocity of about 17 kilometers per second, in 5 billion years Voyager 1 will have traveled approximately 2.7 light years from its current position. That puts it somewhere in the region of 3 light-years from the Sun, still well within what we would broadly consider the solar neighborhood, but far enough that the expanding Sun would be nothing but a very bright star in its sky, if it had a sky, if anyone were watching. The expanding shell of gas that the Sun will eventually eject, the planetary nebula, will disperse over tens of thousands of years and will not travel anything like 3 light-years before it fades. So Voyager 1 will be safe from that in the most purely physical sense. Not that it will matter. The spacecraft will have been dead, scientifically, electrically, functionally, for approximately 4.999999 billion years by then. It will be a piece of metal and gold-plated copper drifting through interstellar space, ancient beyond any category of ancient that human language was designed to express. And yet it will still be there, because in space objects do not rust. They do not decay in the biological sense. They are not subject to wind or rain or the grinding action of geology. In the cold vacuum of interstellar space, protected from most forms of erosion, a metal object can survive for an almost unimaginable span of time. The golden record on Voyager 1's hull is estimated to remain physically intact for at least 1 billion years. The spacecraft itself, though battered over deep time by the occasional impact of interstellar dust particles and bathed in low levels of cosmic radiation, will hold together for far longer than anything built of living matter ever could. Voyager 1 will outlast every human being who has ever lived. It will outlast every building ever constructed. It will outlast every book ever written, every institution ever founded, every civilization ever raised and fallen. It will outlast, in all probability, the human species itself, not because humanity is doomed in the near term, but because 5 billion years is a time span over which everything changes, everything ends, everything transforms into something else. There is a concept in philosophy sometimes called the overview effect. Astronauts who have seen Earth from space, that small, blue, heartbreakingly beautiful sphere hanging in the black, often report a profound shift in perspective, a sudden, visceral understanding that borders and nations and conflicts are constructs laid over a single, fragile, interconnected living world. The distance produces clarity. Thinking about Voyager 1 produces something similar, but on a cosmic scale. When you trace the full arc of its journey, not just the 50 years it has already flown, but the tens of thousands of years it will drift through the Oort cloud, the millions of years it will wander the interstellar medium, the billions of years it will outlast the very star that gave it life, something shifts. The noise of daily life does not disappear exactly, but it is placed inside a context so vast that it takes on a different weight. You are alive right now, in this specific moment in cosmic history, on the only planet known to harbor life, in a solar system whose star is in the quiet, stable middle of its existence. The Sun is not too old, it is not too young, it is not expanding or contracting or in any phase of crisis. It is simply burning, steadily, reliably, as it has, for longer than the Earth itself has existed. And because of that, you are here. You can ask questions, you can feel wonder. You can build machines and name them and track them across the solar system, and cry when their memory chips break and cheer when you fix them from 24 billion kilometers away. That is not ordinary. That is extraordinary. And Voyager 1, in its long, silent journey, is perhaps the clearest proof of it we have ever managed to manufacture. But even knowing all of this, the interstellar medium, the Oort cloud, the dying sun, the golden record, the deep time, there is still one more dimension to this story that we have not fully explored yet. Something closer to home. Something that involves not the distant future, but the next few years. The final active years of a spacecraft that has already given us more than anyone in 1977 dared to hope, because Voyager 1 is still alive. Its transmitter is still warm. Its remaining instruments are still gathering data from a place no instrument has ever been, and the team still caring for it, a group of engineers and scientists who were not even born when it launched, are making decisions right now about how to use its last remaining power as wisely as possible. What are those decisions? What gets turned off? And when? What has the team already sacrificed to keep the most important instruments running a little longer? And what does it actually feel like to be the person who has to send the command that silences, one by one, the senses of the most distant object humanity has ever made? That is where we are going next. And it is a story that is equal parts engineering challenge, philosophical weight, and something that might honestly move you in a way you did not expect a story about a spacecraft to do. There is a building in Pasadena, California, nestled against the foothills of the San Gabriel Mountains, where a small group of people spend their working days doing something that has no real parallel anywhere else on Earth. They are the flight team for the Voyager missions, and their job at this point in history is not exploration in the traditional sense. It is something quieter, more tender, and in its own way more profound. Their job is to keep a dying spacecraft alive for as long as possible, and to make sure that when it finally goes, it goes having given everything it had left. The team is small, surprisingly small given what they are responsible for. NASA has gradually reduced the resources dedicated to the Voyager missions over the decades as the spacecraft have aged, and the scientific return, while still genuinely valuable, has had to be weighed against the cost of maintaining a dedicated operations team. At various points in the mission's history, there have been genuine fears that funding would be cut entirely, that the plug would simply be pulled on the grounds that the money could be better spent elsewhere. So far, those fears have not materialized. The scientific community has consistently argued successfully that the irreplaceable nature of the data justifies the continued investment. Where else are you going to get measurements from inside the local interstellar medium? You cannot replicate that. You cannot simulate it well enough to make the real data redundant. But the team is lean. Many of the engineers who work on Voyager today were not born when it launched. They learned to work with systems that were designed and built before personal computers existed, using documentation written in an era when the idea of a spacecraft still transmitting data from interstellar space was purely theoretical. Some of the original technical documents are typed on actual typewriters. The knowledge required to operate these spacecraft, the deep institutional, hands-on understanding of how these particular systems behave after nearly 50 years of continuous operation, lives in a relatively small number of people, and that is its own quiet vulnerability. One of the most striking things about how the Voyager team operates is the discipline required to work within such extreme constraints of time and uncertainty. Every decision about what to do with the spacecraft has to account for that 45-hour round-trip signal delay. But beyond the time lag, there is another constraint that has been tightening for years and will continue to tighten until the mission ends: power. The radioisotope thermoelectric generators aboard Voyager 1, the RTGs, those remarkable devices that convert the heat from decaying plutonium-238 into electricity, are not what they once were. When the spacecraft launched, they produced roughly 470 watts of electrical power. Every year since then, the plutonium has continued to decay, and the output has declined at a rate of roughly 4 watts per year. By the mid-2020s, the available power had fallen to somewhere in the region of just over 200 watts. Less than half of what was available at launch, 200 watts. That is roughly the equivalent of 2 old-fashioned incandescent light bulbs. That is the total electrical budget for every system aboard Voyager 1, the transmitter, the computers. the heaters that keep critical components from freezing in the cold of interstellar space, and whatever science instruments are still operating. Every single watt matters. The team has to balance the power budget with extraordinary care because there is no margin, there is no reserve. If the numbers do not add up, something has to be turned off. And so, over the years, instruments and systems have been shut down one by one, not because they failed, but because the power simply was not there to keep them running. Each shutdown is a deliberate choice, made after careful analysis, to sacrifice one thing in order to preserve another. The plasma subsystem heater was turned off years ago. The cosmic ray subsystem has been powered down. Other components have been switched off or put into reduced power modes. Each time it represents the loss of a capability that will never return. The spacecraft cannot be restarted like a car. What goes off stays off. The decisions about what to keep running and what to shut down are not made lightly. They involve the entire scientific community that has a stake in Voyager 1's data, researchers from universities and institutions around the world who rely on the spacecraft's measurements for their work. Every time an instrument is considered for shutdown, there are discussions, papers, arguments, pleas. People who have spent their careers building models based on Voyager 1's data make the case for keeping their particular instrument alive a little longer. And the team has to weigh those scientific arguments against the cold arithmetic of the power budget. The instruments that have survived this long have done so because they were judged to be providing the most scientifically irreplaceable data. The magnetometer, which measures the magnetic field in the local interstellar medium, has remained operational because the magnetic field data is continuous. You cannot simply turn it off and turn it back on and expect to have filled the gap. The plasma wave subsystem, which detected those unexpected oscillations in the interstellar plasma, the faint hum of the space between stars, has also remained active for the same reason. These are measurements you have to take constantly to understand the dynamics of the environment. The decisions will keep coming. As the power continues to drain away at its steady rate of roughly 4 watts per year, the team will eventually face choices that leave no good options. At some point, they will have to choose between the heaters that keep the transmitter from becoming too cold to function and the instruments themselves. At some point, the transmitter will need more power than is available if the science instruments are running, and then the last instrument will go dark, and then, sometime after that, the transmitter itself will fall silent. Current projections suggest that Voyager 1 will lose the ability to operate any science instruments sometime around 2025 to 2030, depending on how carefully the power is managed. The transmitter may last a little longer, perhaps into the early to mid-2030s. But by roughly 2036, the most optimistic estimates suggest Voyager 1 will be completely silent. 46 years, perhaps a few more, of continuous contact with the most distant human-made object in existence, and then nothing. There is a woman named Suzanne Dodd, who has served as the project manager for the Voyager interstellar mission for a significant part of its recent history. In interviews, she has spoken about what it is like to be responsible for these spacecraft at this stage of their lives. She describes the team's relationship with Voyager 1 and 2 in terms that go beyond the professional. There is genuine affection, genuine grief already anticipated for the moment the signal will be lost for the last time. These are not just machines to the people who care for them. They are something closer towards, or companions, entities whose lives the team has been entrusted to extend as far as possible, with full knowledge that the end is coming and the best they can do is delay it with intelligence and care. That emotional relationship is not irrational, it is, in fact, deeply human. the impulse to form attachments to the things we build, especially things that represent our collective ambition and curiosity and courage, is not a weakness. It is part of what drives us to build them in the first place. The engineers who cried when Voyager 1's signal became coherent again after the memory chip repair were not being sentimental. They were responding to something real, the restoration of a connection that matters, to science and to the human story both. There is another dimension to this that is worth dwelling on for a moment. Because when we talk about the team at JPL managing Voyager 1's final years, we are not just talking about the technical challenge, we are talking about an act of custodianship for something that belongs, in a meaningful sense, to all of humanity. Carl Sagan, when he championed the Golden Record project, understood this. Voyager 1 is not American, not in any way that ultimately matters. Yes, it was built by NASA, funded by the United States government, launched from American soil, but the images on the Golden Record are of humans, not Americans. The music on it is from every corner of the world. The greetings are in 55 languages. The mathematics used to explain where it came from is universal. Whoever put it together understood, at least in that moment, that they were not sending a national achievement into the cosmos. They were sending a human one. And so when the team at JPL works through the night to debug a 47-year-old memory chip, or agonizes over which instrument to power down next, or sends a command that will take 22.5 hours to arrive at its destination, they are doing it on behalf of all of us, on behalf of the species, on behalf of every person who has ever looked up at the night sky and wondered what is out there and whether we will ever reach it. Now, here is something that does not come up often in discussions of Voyager 1, but that I think deserves a moment of serious attention. We are at a genuinely unique point in history with respect to this mission. The spacecraft is still alive, it is still transmitting. The people who have the knowledge and skills to communicate with it are still working. The Deep Space Network, the system of enormous radio antennas around the world that NASA uses to communicate with distant spacecraft, is still operational and capable of receiving Voyager 1's signal, which by the time it arrives at Earth has been attenuated to a power level of roughly 10 to the minus 17 watts. That is 0.00001 femtowatts. It is so faint that it requires the largest antennas in the network, dishes up to 70 meters across, and extremely sensitive receivers just to detect it at all. This window, the window during which we can still hear from Voyager 1, will close within our lifetimes. Many of the people watching this video today will live to hear the news that the last signal has been received. That is not a distant, abstract event. It is something that is genuinely going to happen, probably within the next 10 to 15 years, to a spacecraft that launched less than 50 years ago. And when that signal goes quiet, something irreversible will have happened. We will have lost the ability to communicate with the most distant object humanity has ever sent into the cosmos. We will know roughly where it is. Orbital mechanics will keep the trajectory calculable for a very long time, but we will not be able to hear it. We will not be able to adjust it. We will not be able to receive any more data from it. The conversation, which has been running continuously since 1977, will simply stop. That moment deserves to be marked. It deserves to be felt, not just as a scientific milestone and not just as a piece of aerospace history, but as something more elemental, the end of a conversation that humanity started with the universe itself. Not a successful conversation in the sense of receiving a reply, but a conversation nonetheless, one that said, in the most concrete possible terms, we are here, we are curious, we built something and sent it out, and we listened to it faithfully for as long as we could. What comes after that silence is in some ways the most remarkable part of the whole story, because the silence will not be the end. Voyager 1 will keep moving, The golden record will keep drifting. The journey will continue for billions of years after the last human being who remembers its launch has turned to dust. And in that extraordinary, vertiginous gap between the end of the signal and the incomprehensible vastness of what comes after, there is a question waiting that might be the most important question the whole Voyager story asks us to consider. Not what will Voyager 1 find, because it will find nothing. It is not designed to find anything. It has no way of searching, no way of stopping, no way of sending back new data once the power is gone. The question is different. The question is, what does it mean that we sent it at all? What does it say about us, about this species, on this planet, at this moment in cosmic time, that we built something and launched it and tracked it faithfully across 50 years and 25 billion kilometers and repaired it from across the solar system and listened to it until the very last whisper of its signal faded below the noise floor of our best instruments? That is the question Part 6 is going to sit with. Because the answer, I think, is not what you might expect, and it connects the story of Voyager 1 to something much closer to home, to the question of what we are and what we might become, and whether the universe we are so slowly beginning to explore is one that was, in any sense, waiting for us to arrive. Let us start with a number that, depending on how you look at it, is either deeply comforting or profoundly unsettling, and possibly both at the same time. There are estimated to be somewhere between 200 billion and 400 billion stars in the Milky Way galaxy alone. Of those, astronomers now know, thanks largely to data from missions like the Kepler Space Telescope and its successor TESS, that the vast majority host planetary systems. The fraction of stars with planets is not some rare exception. It is the rule. Planets are common. They form naturally, almost inevitably, from the disks of gas and dust that surround young stars as they coalesce. Our solar system is not special in that regard. It is one example of a process that has been happening across this galaxy for billions of years. Of those hundreds of billions of planetary systems, a significant fraction will contain planets in the so-called habitable zone, the range of orbital distances where liquid water can exist on a surface. Current estimates suggest there may be tens of billions of potentially habitable rocky planets in the Milky Way alone, tens of billions in just our galaxy, and there are estimated to be somewhere in the region of 2 trillion galaxies in the observable universe. So the raw numbers, at first glance, seem to scream that we cannot possibly be alone. The universe is simply too large, too old, too full of the right ingredients for life to have arisen only once, on one planet, around one star, in one corner of one galaxy. And yet we have been listening. For decades now, astronomers and researchers have been scanning the sky for signals, radio transmissions, laser pulses, any kind of structured electromagnetic emission that might indicate the presence of a technological civilization somewhere out there. The search for extraterrestrial intelligence, SETI, has been running in various forms since 1960, 60+ years of listening, and the result, so far, is silence, an almost total, unbroken silence. A few anomalous signals have flickered into view over the years, raised hearts briefly, and then turned out to have mundane explanations or simply never repeated. Nothing has arrived that unambiguously says, we are here too. This tension between the mathematical expectation that intelligence should be widespread and the observational reality of complete silence is one of the deepest unsolved puzzles in science. It has a name, the Fermi paradox, named after the physicist Enrico Fermi, who in 1950 famously asked, during a lunchtime conversation with colleagues, if the universe is so vast and so old and so full of potentially habitable worlds, where is everybody? There are many proposed answers to Fermi's question. Some are reassuring, some are terrifying, most are humbling. One possibility is simply that interstellar distances are so enormous that communication and travel between civilizations is effectively impossible on any timescale that matters. Even radio waves, traveling at the speed of light, take 4 years to reach the nearest star. A signal sent to a civilization 1,000 light-years away would take 1,000 years to arrive and another 1,000 years to receive a reply. The galaxy might be full of civilizations that are simply too far apart and too short-lived to ever make contact. In this scenario, the silence is not evidence of absence. It is evidence of distance. Another possibility is that life is genuinely rare, not the chemistry of life, which seems to arise naturally given the right conditions, but complex, intelligent, technological life. Maybe the steps between simple microbial life and a civilization capable of building radio telescopes involve so many unlikely transitions: the evolution of multicellular organisms, the development of nervous systems, the emergence of language and abstract thought and technology, that even in a galaxy of hundreds of billions of stars, those transitions have happened only a handful of times, or perhaps only once. A third possibility is darker. Sometimes called the Great Filter, it proposes that there is some barrier, some step in the development of civilizations that almost nothing gets through, a catastrophic obstacle that civilizations typically do not survive. The question, and it is one that should genuinely make you pause, is whether that filter lies behind us or ahead of us. If it lies behind, if the great improbability was in the emergence of life itself or in the leap to complex multicellular organisms, then we have already passed through it and the future is open. If it lies ahead, if there is something that technological civilizations consistently do to themselves, some threshold they cannot cross, then the silence of the cosmos might be a warning, a graveyard census. Voyager 1 does not answer any of these questions directly, but it asks them more sharply than almost anything else we have ever built. Because Voyager 1 is, among other things, our most honest attempt at communication across the void. The golden record is not a scientific instrument, it is a hand extended into the dark, and the fact that it will almost certainly never be found, the fact that even if it were found, after billions of years of drift, any civilization capable of detecting it would already possess technologies so far beyond ours that the record would be more archaeological artifact than introduction, does not diminish the gesture. It deepens it, because the golden record was never really meant for aliens, not primarily. Carl Sagan understood this. The act of deciding what to include, of sitting down and asking the question, what are we, and how do we show it to someone who knows nothing about us, was itself an exercise in self-understanding. What music represents humanity? What images? What sounds? What mathematics? The answers to those questions say something profound about what we value, what we find beautiful, what we think is essential about being alive on this particular world. The record includes the sound of rain, of surf, of wind, of a mother whispering to her newborn. It includes music that makes people weep and music that makes them dance. It includes greetings in languages, some of which are now nearly extinct. It includes a photograph of a man licking an ice cream cone, a family gathered around a dinner table, a woman nursing an infant, a gymnast mid-flight, humans eating, running, leaping, building, the UN building in New York, the Great Wall of China, a supermarket, a traffic jam. Somewhere in that process, looked at the traffic jam photograph and said, yes, include that. That is us too. Not just our best moments, not just our achievements, us, ordinary, daily, beautifully mundane us. That decision, that insistence on honesty, on including the full texture of human life rather than just the highlights, is one of the most quietly moving things about the entire Voyager project, and it connects to something important about what the mission ultimately represents. We are a species that has been on this planet for a cosmically negligible amount of time. modern Homo sapiens, anatomically and behaviorally, have existed for perhaps 300,000 years. Agriculture, the foundation of civilization, is roughly 12,000 years old. Writing is about 5,000 years old. The Industrial Revolution began less than 300 years ago. The entire age of spaceflight is less than 70 years old. In cosmic terms, we are newborns. The universe is 13.8 billion years old. If that history were compressed into a single calendar year, humanity's entire existence would occupy the last few seconds of December 31st. The space age would be a fraction of a single heartbeat. And yet, in that vanishingly brief moment, we built something that has left the solar system. We designed and constructed a machine using the physics we had only recently worked out, powered by the radioactive decay of elements forged in ancient stellar explosions, carrying music and mathematics and the sound of a mother's voice, and we threw it out of the only home we have ever known, into the vast dark between the stars. That is not a small thing. That is, by any reasonable measure, one of the most extraordinary things any species has ever done. And we did it not because it was necessary for survival, not because it generated profit, not because anyone ordered us to. We did it because we are the kind of creature that looks at the edge of the known world and instinctively wants to see what is beyond it. That instinct, call it curiosity, call it the explorer's drive, call it the refusal to accept that the horizon is a boundary rather than an invitation, is perhaps the defining characteristic of our species. It is what took our ancestors out of Africa and across continents and oceans. It is what built the ships that crossed the Atlantic and the Pacific. It is what drove the expeditions to the poles, the climbs to the summit of every mountain. It is what put human beings on the moon less than a century after the first powered aircraft flight. And it is what launched Voyager 1 in 1977 with an instrument package designed not just to study Jupiter and Saturn, but to keep going, to go as far as the power held out, to see what was on the other side of the heliosphere, to step, in a tiny but real way, out of the cradle. The philosopher and writer Timothy Ferris, who helped produce the Golden Record, once wrote about the strange feeling of working on it. The awareness that this object, this modest disk of gold-plated copper, would outlast every human institution, every building, every language, every nation, that it would be drifting through the galaxy when the sun had long since expanded and faded, that it was, in a real sense, the most permanent thing humanity had ever made. Not because it was built to last, but because the environment it was heading into has nothing to destroy it. The most permanent thing we have ever made is a record of our music, a photograph of a traffic jam, the sound of the wind. There is a version of this story that is melancholy, the vast silence, the impossibility of the distances, the certainty that Voyager 1 will never be found, never answer any question about whether we are alone, never confirm or deny the existence of anyone else out there listening. The knowledge that the spacecraft will go dark within our lifetimes, that the conversation will end, that the most we can hope for is that something we built will drift for billions of years through a universe that may never notice it was there. That version is real. Those feelings are legitimate. The cosmos does not owe us contact. The universe does not arrange itself around our emotional needs. The silence is real, but theirs is another version, and it lives inside the same facts. In this version, the silence is not a verdict. It is a frontier. The universe is 13.8 billion years old, and we have been technologically capable of detecting signals from space for less than a century. We have surveyed only a tiny fraction of the sky at a limited range of frequencies for a blink of cosmic time. Our instruments are improving, our methods are diversifying. We are learning to look for biosignatures in the atmospheres of exoplanets, chemical signs of biological processes detectable from light years away. We are building telescopes that will be able to directly image the surfaces of worlds orbiting nearby stars. We are, in every meaningful sense, just beginning. And Voyager 1 is the physical embodiment of that beginning. It is the first step of a journey that, if our species endures, will eventually take us to places we cannot yet imagine. It is proof that we can leave, that the solar system is not a sealed container, that the physics works. That determination and intelligence and the willingness to wait 45 hours for an answer can carry something made of human hands to the edge of the known universe and beyond. The Voyager mission was conceived in an era of extraordinary ambition. The 1970s were not an obviously optimistic time. Vietnam, Watergate, oil crises, the long shadow of the Cold War. And yet, in the middle of all of that, a group of scientists and engineers proposed sending 2 spacecraft on a grand tour of the outer planets, using a rare planetary alignment that would not recur for another 175 years. And they got it funded and built and launched, and it worked. All of it worked. Every flyby, every image, every reading, the gravity assists, the course corrections, the decades of faithful transmission. It all worked. That is not just a story about engineering. It is a story about what human beings are capable of when they refuse to be bounded by the merely practical, when they look at what is possible rather than what is comfortable, when they send something out not because they know it will succeed, but because the attempt itself is worth making. Voyager 1 is still out there, right now, moving away from us at 17 kilometers per second, carrying its golden record, returning its last data, tended by a small team of dedicated people in a building in Pasadena who know they are part of the final chapter of something that began before most of them were born, and the story is not over yet. There are still things to discover, still data coming in, still decisions to be made about how to spend the last of the power, the last of the operational life, the last of the signal. In the next part, we are going to look at exactly that, the final scientific chapters of the Voyager 1 mission, what the team is prioritizing in its last active years, and what the very last transmission will look like when it finally arrives. Because that moment, whenever it comes, will be unlike any other moment in the history of human exploration, and it deserves to be understood fully before it happens. Picture this. Somewhere in the Mojave Desert and in Madrid, Spain, and near Canberra, Australia, there are dishes, enormous ones. The largest of them stretches 70 meters across, wider than a 20-story building is tall. They are pointed at a precise location in the sky, tracking a signal so faint that it would take approximately 22,000 billion of them stacked together to power a single LED light bulb. These are the antennas of the Deep Space Network, and right now, today, they are listening to Voyager 1. The signal arrives. It has been traveling for over 22 hours. It left a spacecraft roughly 25 billion kilometers away, generated by a transmitter running on about 22 watts of power, roughly the same as a dim refrigerator bulb. By the time it crosses that incomprehensible distance and arrives at Earth, it has spread out so far, diluted across such an enormous sphere of space, that detecting it at all is an act of technological heroism, and yet the dishes hear it every day. Still, that signal carries data, engineering telemetry, readings about the spacecraft's own health, its temperatures, its power levels, the status of its systems, and, from the instruments still running, actual science. Measurements of magnetic field strength and direction, readings of plasma wave activity, the faint but real and irreplaceable fingerprints of a region of space no other instrument has ever touched. This is the daily reality of the Voyager 1 mission in its final years. Not dramatic, not cinematic, quiet, meticulous, and extraordinary in the most understated possible way. Let us talk about what the science team is actually prioritizing right now. because understanding that tells you something important about what the mission's final years are for. The magnetometer is considered by many researchers to be the single most valuable instrument still operating aboard Voyager 1. The reason is continuity. Magnetic field measurements are only fully meaningful when they are continuous, when you have an unbroken record of how the field behaves over time across changing conditions. A gap in the data is not just an inconvenience, it can make years of surrounding measurements harder to interpret. So the magnetometer runs, day after day, year after year, recording the magnetic environment of the local interstellar medium with a patience and consistency that no human observer could match. What it is finding continues to surprise researchers. The magnetic field in the local interstellar medium is not uniform. It has structure. It has variations that reflect the history of the space our solar system is currently moving through. The echoes of ancient stellar winds, the remnants of supernova shockwaves that passed through this region thousands or millions of years ago. Every light year our solar system travels through the galaxy, and we are traveling, the whole solar system orbiting the galactic center at about 230 kilometers per second. We are moving through a slightly different environment. The magnetic field Voyager 1 is measuring right now is a snapshot of one particular patch of that environment, a patch our solar system has not passed through before and will not pass through again. That is irreplaceable in the most literal sense. You cannot go back and take that measurement later. The plasma wave subsystem is the other instrument the team is working hard to keep alive. It was this instrument that detected the persistent oscillations in the interstellar plasma, that faint, continuous hum that researchers described as the background voice of the space between stars. Those oscillations have continued and continued to be measured and continued to yield information about the density and temperature of the plasma in the local interstellar medium. Information that feeds directly into models of how the heliosphere interacts with its surroundings, models that have implications for every star system in the galaxy, with planets worth caring about. There is something almost meditative about the image of this instrument, a sensor on a spacecraft nearly 50 years old, drifting through the dark between the stars, faithfully recording a hum that has been there since long before our solar system existed, sending those readings home at the speed of light to people sitting at computers in California, who then publish papers that other researchers around the world use to refine their understanding of how the universe is put together. The decisions about power allocation in these final years have become increasingly painful. Every watt redirected to a heater is a watt taken away from an instrument. Every instrument kept running draws power away from the systems that keep the spacecraft warm enough to function. The team has already made choices that earlier generations of mission controllers would have found agonizing. Some instrument heaters have been turned off, accepting the risk that the instruments themselves might be damaged by the cold. So far, the spacecraft has proven more resilient than feared, but the margins are shrinking. There have been serious internal discussions about which instrument should be the last one running, which measurement is so important that it justifies keeping everything else off in order to power it for as long as possible. The magnetometer is the leading candidate for the reasons already described. Its data is continuous, its value is undisputed, and it draws relatively little power compared to some other systems. The team's best current thinking is to keep it running as late as possible, accepting the gradual shutdown of everything else as the power budget demands. At some point, and the projections suggest this will happen in the late 2020s or early 2030s, the transmitter itself will face a crisis. The transmitter is the most power-hungry essential system on the spacecraft. It is what converts the electrical power from the RTGs into the radio signal that crosses 25 billion kilometers to reach our antennas. When there is no longer enough power to run both the transmitter and any science instrument simultaneously, the science will end. The spacecraft will continue transmitting, just engineering data, the vital signs of a machine with nothing left to measure, until even that is no longer possible, and then one day the signal will simply stop arriving, not with a dramatic final message, not with a farewell, just silence where there was signal, a gap in the data stream that deepens into absence. The team at JPL has thought carefully about this moment, not just the technical reality of it, but the human one. Suzanne Dodd has spoken in interviews about the importance of documenting everything, not just for scientific posterity, but for the historical record. The Voyager mission represents something genuinely unique in human history, and the people who have lived inside it, who have spent their careers tending to these two spacecraft, carry knowledge and experience that needs to be preserved. Oral histories are being recorded, technical archives are being compiled. The institutional memory of the mission is being captured as carefully as the engineering itself. There is something quietly poignant about that parallel effort. On one hand, the team is working to extract every last possible watt of scientific value from the spacecraft before it goes dark. On the other, they are working to preserve the memory of the mission itself, to ensure that when the signal ends, the story does not. That future engineers, future scientists, future human beings who might one day send something farther and faster will be able to look back at Voyager 1 and understand not just what it did, but how it felt to be the people who did it, because that matters. The emotional texture of exploration matters. The fact that engineers wept when the signal became coherent again after the memory chip repair, that matters. The fact that people who were not born when this spacecraft launched have given years of their professional lives to keeping it alive, that matters. The fact that someone will one day send the last command to a spacecraft that has been flying for over 50 years, knowing it will take 22 hours to arrive and that there will be no meaningful reply, that matters. History is not just data, it is people. It is the experience of being alive at a particular moment, doing a particular thing, caring about it in a particular way. And the Voyager mission, in all its quiet, extraordinary, decades-long duration, is one of the most human things we have ever done. Let us talk about what happens on the day the signal finally stops, not the engineering of it. We have covered that. The experience of it, for most people on Earth, it will be a news story. A brief moment of coverage, perhaps a few minutes on a broadcast, a handful of headlines, and then the next thing. The world will keep turning, markets will open, traffic will flow, children will go to school. The loss will be real but abstract for most people. The end of something they perhaps knew existed, but never thought much about in daily life. For the team at JPL, it will be different. For the researchers who have spent careers analyzing Voyager data, it will be different. For the engineers who have spent years figuring out how to keep a 40-something-year-old spacecraft running on a power budget smaller than a household lamp, it will be different. For them, it will be a genuine ending, a grief that has been anticipated for years. That does not make it easier when it arrives. There is a phenomenon that psychologists sometimes call anticipatory grief. The mourning that begins before the loss, when you can see it coming but cannot stop it. The Voyager team has been living with a version of this for years. Every instrument shutdown is a small death. Every power reduction is a step closer. The final silence has been visible on the horizon for a long time, getting gradually closer, growing gradually more real. And when it comes, when the last data point arrives, when the last engineering packet crosses the 25 billion kilometer gap and is received and logged and there is no next packet, Someone in that building is going to understand, in the most immediate and personal way, that a 50-year conversation has just ended, that a machine they helped keep alive through ingenuity and dedication and care has gone silent for the last time. What do you say at a moment like that? What do you do with the feeling? Perhaps you do what humans have always done at the edges of the knowable. You sit with it, you let it be as large as it is. You resist the urge to immediately fill the silence with something else, and you let it mean what it means, the end of the closest thing to a human presence that has ever existed in interstellar space. The final chapter of the most audacious journey our species has ever undertaken. And then, maybe, you start thinking about what comes next, because here is the thing. The end of Voyager 1 as a communicating spacecraft is not the end of human ambition in deep space. It is, in a very real sense, a beginning, or rather, it is one point in a continuum that started long before 1977 and will extend long after the signal goes quiet. Already, mission planners and scientists are thinking about what it would take to send a successor. An interstellar precursor mission, a spacecraft specifically designed to study the heliosphere and the local interstellar medium, with modern instruments, modern power systems, modern communications technology, aimed at eventually surpassing Voyager 1's distance and continuing the measurements from beyond the heliopause with equipment designed for the purpose rather than adapted from a planetary flyby mission. Such a mission has been discussed seriously in NASA planning documents for decades. It has never quite made it to the top of the priority list. The cost, the timescales, the political challenge of funding something whose primary scientific payoff would come 30 or 40 years after launch have all worked against it. But the scientific case for it is strong, and it grows stronger as Voyager 1 approaches its end and takes with it the only in situ measurements we have of the interstellar medium. Beyond that, there are more speculative but genuinely serious proposals for faster interstellar probes. The Breakthrough Starshot initiative, announced in 2016, proposes using powerful ground-based lasers to accelerate a fleet of tiny, lightweight spacecraft, each no bigger than a postage stamp, to roughly 20% of the speed of light. At that velocity, such a probe could reach the Alpha Centauri system in approximately 20 years. It could send back images and measurements of any planets there. It would be the first human-made object to actually travel to another star system during a human lifetime. The technical challenges are enormous. The engineering problems are genuinely hard. But the concept is based on real physics, and serious researchers are working on it. The spirit behind it is identical to the spirit that put Voyager 1 on its trajectory in 1977. The refusal to accept that the stars are beyond reach, the insistence that the universe is not a backdrop but a destination. Voyager 1 will not be there to see any of that. It will be dark and silent, drifting at 17 kilometers per second through the Oort cloud, carrying its golden record through the long, cold dark. But in a sense, it will have made it possible, not technically, but spiritually. It will have demonstrated beyond any doubt that sending something beyond the solar system is achievable, that the physics works, that the dedication and patience required are within human capability, that the conversation with the cosmos, even if it goes unanswered, is worth having. Every future mission to the outer solar system, every proposal for an interstellar precursor, every serious discussion of reaching another star, all of it stands on the foundation that Voyager 1 laid. All of it draws, in some measure, from the proof of concept that a small team of scientists and engineers provided in 1977 when they pointed a spacecraft at the outer planets and said, "Let us see how far it can go. How far can it go? Farther than anyone imagined, farther than any human being will live to see the end of, farther than the signal can carry, farther than memory eventually, farther than the star that launched it, farther, perhaps, than anything else we will ever make. If you're still here, you're not the kind of person who settles for easy answers. Don't forget to subscribe and give this video a like. Every day we tackle the questions that actually keep you up at night. And we never come back empty-handed. There is a photograph. You may have seen it. It was taken on February 14th, 1990, at the request of Carl Sagan, who spent years lobbying NASA to turn Voyager 1's camera around one last time before it was powered down. The spacecraft was approximately 6 billion kilometers from the Sun at that point, well beyond the orbit of Neptune, heading outward into the dark. And when the camera turned and looked back, it captured something that changed how many people understood their place in the universe. Earth appears in that image as a single pixel, a pale blue dot, barely distinguishable from the scattered light of the Sun, suspended in a ray of sunlight caught by the camera's lens. The entire planet, every mountain and ocean and city and battlefield, every person who has ever lived, every piece of music ever composed, every war ever fought, every act of love or cruelty or courage or cowardice in the entire span of human history, all of it fits inside one pixel. One pale blue dot in the vastness of a solar system that is itself an inconceivably small part of a galaxy that is itself one of 2 trillion galaxies in the observable universe. Sagan wrote about that photograph in terms that have never been surpassed for their combination of scientific precision and emotional depth. He wrote that our planet is a lonely speck in the great enveloping cosmic dark, that in our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves, that it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we have ever known. Those words were written over 30 years ago. They have not aged, they have not dated. If anything, they have become more urgent, because everything Voyager 1 has taught us since then, everything about the heliosphere and the interstellar medium and the vast emptiness between stars, only deepens the truth that Sagan was pointing at. We are here, we are small, we are alone as far as we can tell in a universe that offers no guarantees and no safety net. And what we do with that knowledge matters. Now let us take the widest possible view. Let us zoom out to a scale that makes even the interstellar medium feel intimate. Let us look at where Voyager 1 fits in the story of the galaxy itself. The Milky Way is a barred spiral galaxy, a flattened disk of stars, gas and dust roughly 100,000 light-years across, with a central bar-shaped region of densely packed stars surrounded by 4 major spiral arms. Our Sun sits in one of those spiral arms called the Orion Arm or the Local Spur, approximately 26,000 light-years from the galactic center. We orbit that center at about 230 kilometers per second, a speed that sounds enormous until you realize that at that velocity, a full orbit of the galaxy takes approximately 225 to 250 million years. That period is sometimes called a cosmic year or a galactic year. In the roughly 4.6 billion years since our solar system formed, it has completed somewhere around 20 galactic orbits. It has been around the center of the Milky Way 20 times. During each of those orbits, it has passed through different regions of the galaxy, regions of varying stellar density, varying concentrations of gas and dust, varying exposure to the radiation environments created by nearby supernovae and other violent events. The history of life on Earth is in part a history of our solar system's journey through the galaxy and the changing cosmic environment that journey produced. Voyager 1, from the perspective of the galaxy, has moved essentially nowhere. The distance it has traveled, 25 billion kilometers, is a fraction so small relative to galactic scales that it does not even register. The nearest star is 4.2 light-years away. The galaxy is 100,000 light-years across. Voyager 1 has covered about 0.0000003 light-years from where it started. On a galactic map, its position and its origin are the same point, and yet, from the perspective of what it represents, from the perspective of the intelligence that built it, Voyager 1 has already crossed one of the most significant boundaries in the history of life on Earth. It has left the solar system. It has entered interstellar space. It has crossed the threshold from the domain of our star to the domain of the galaxy. No living thing has ever done that before. No molecule that was once part of a living organism has ever been carried to that distance by intent, by design, by the deliberate act of a thinking species. Here is something worth sitting with for a moment. Life on Earth has been present for roughly 3.8 billion years. In all that time, through the emergence of single-celled organisms, through the explosion of multicellular life, through the age of the dinosaurs and their extinction, and the long, slow rise of mammals and eventually primates and eventually us. In all of that vast biological history, not one molecule of biology left the solar system, not one. The gravity of the sun held everything here, every living thing that ever existed, every organism that ever breathed or swam or crawled or flew within the warm inner pocket of the heliosphere. Voyager 1 changed that. Not biologically, there is no life aboard it, but it was built by life. It was designed, manufactured, programmed, launched, tracked, and repaired by living organisms. It carries the imprint of biology in every circuit and every line of code and every image etched onto the golden record, and it is outside the solar system. For the first time in 3.8 billion years of life on this planet, something shaped by biology exists beyond the heliosphere. That is a threshold, a genuine one, and thresholds in the history of life tend to matter. The first organism to crawl out of the ocean onto land was crossing a threshold. The first primate to chip a stone into a tool was crossing a threshold. The first human to sail beyond sight of land was crossing a threshold. We do not always recognize thresholds when we cross them. We tend to see them clearly only in retrospect, when we can look back and see how everything that came after was shaped by the crossing. We are close enough to the Voyager threshold that it is still difficult to see its full significance. But I suspect, and I think the science supports this, that when the history of life in this universe is eventually written, if it ever is, the moment a biological species first extended its reach beyond its home star system will be considered one of the defining transitions in the story of matter becoming self-aware and reaching outward. Now let us go further still. Let us look at the deep future of the cosmos itself, not just the 5 billion year future of our solar system, which we explored in Part 4, but the truly long view. The view that makes even stellar evolution look brief. The universe is currently about 13.8 billion years old. It is in what cosmologists sometimes call the stelliferous era, the age of stars. Across this era, which began a few 100 million years after the Big Bang and will last for roughly 100 trillion years, the universe is lit by the nuclear fires of billions of stars. It is a relatively bright, relatively active period. New stars are still forming, old ones are dying, planetary systems are coming and going. The raw ingredients for life are being assembled and scattered by stellar processes across the galaxy. 100 trillion years is so far beyond human intuition that any comparison feels inadequate. It is roughly 7,000 times the current age of the universe. During that entire span, stars will slowly exhaust the available hydrogen fuel in the galaxy. Star formation will gradually slow. The largest, most massive stars will burn brilliantly and die quickly in millions of years. Smaller stars, the red dwarfs, which make up the vast majority of stars in the galaxy, will burn slowly and dimly for tens of trillions of years. The last stars to die will be these tiny, cool, miserly red dwarfs, guttering out one by one over the course of unimaginable time. After the last star dies, the universe enters what cosmologists call the degenerate era. The stellar remnants, white dwarfs, neutron stars, black holes persist. White dwarfs slowly cool, neutron stars spin down, black holes grow by swallowing whatever falls into them. This era lasts for an almost incomprehensible span, on the order of 10 to the power of 40 years, a number so large that writing it out in full would take longer than the current age of the universe. And where is Voyager 1 during all of this? Still moving, still drifting, at 17 kilometers per second, through the dark between stars, through the gradual death of the galaxy's stellar population, through the cooling and fading of the white dwarfs, the golden record still attached, the cameras still pointing, sightlessly, at nothing. Eventually, and here the physics becomes genuinely strange, even the protons that make up the metal of the spacecraft may decay. Current physics predicts that protons are not truly stable, that given enough time they will spontaneously transform into lighter particles. The estimated timescale for proton decay, if it occurs, is on the order of 10 to the power of 34 years or more. That is a timescale so vast that the entire current age of the universe is less than a rounding error. But if protons do decay, if matter itself is ultimately impermanent on the longest timescales, then eventually, even Voyager 1 will dissolve, not into nothing, but into lighter particles, photons, energy, diffusing into an increasingly cold and dark universe. The most permanent thing we have ever made will, on the longest possible timescale, cease to exist as a structured object. The information it carries, the music, the images, the mathematics, will disperse. Does that make it meaningless? Does the eventual dissolution of Voyager 1 in the unimaginably remote future diminish what it is right now? No. And the reason it does not is the same reason that the brevity of a human life does not make a human life meaningless. The question of meaning does not live at the scale of proton decay timescales. It lives at the scale of experience, of connection, of the relationship between minds and the universe they find themselves in. Right now, at this moment in cosmic time, there is a spacecraft moving through the local interstellar medium. It was built by creatures who evolved from stardust on a rocky planet orbiting an ordinary star. Those creatures looked up, wondered what was out there, built something to go and find out, and then spent 50 years listening to what it reported back. When it broke, they fixed it. When it ran low on power, they made careful, painful choices about how to spend what was left. When it sent back data about the faint hum of the space between stars, they published papers, refined their models, deepened their understanding of the universe. That is meaning, not cosmic meaning. The universe does not assign meaning, but human meaning, which is the only kind we have access to, and which turns out to be more than enough. Voyager 1 is meaningful because the people who built it cared about what it would find. It is meaningful because the data it returns is genuinely new knowledge about a universe we are only beginning to understand. It is meaningful because it carries a record of our music and our voices and our world, sent outward as an act of pure, impractical, irrepressible hope. It is meaningful because it crossed a boundary, the heliosphere, that no living thing had ever crossed before, and because in doing so it proved, physically and irrefutably, that the solar system is not a cage. Sagan's pale blue dot photograph was taken because one scientist refused to let the camera be turned off without looking back one last time. That impulse, to turn around, to see where you came from, to hold the whole picture in your mind before moving on, is one of the most distinctively human things there is. It is why we write history. It is why we build museums. It is why we tell stories. This video is part of that same impulse, the attempt to hold the whole story of Voyager 1 in mind, not just the engineering, not just the science, but the human meaning of it. The fact that it was built by people who knew they would never see it reach its destination, that it was launched into a journey with no arrival, that it carries a message in a bottle thrown into the largest ocean imaginable, with full knowledge that no reply is expected, and yet they threw it. And we are still listening, we are still here. The pale blue dot is still here, and somewhere out there, roughly 25 billion kilometers away, moving farther every second, a small golden record is drifting through the dark, carrying the sound of the wind and the surf and a mother's voice into a universe that may never hear it, but we made it, we sent it. We cared enough to try, and in the story of how matter came to know itself, that might be the most important sentence ever written. There is a particular kind of person who ends up working on a mission like Voyager, not a type defined by background or nationality or even academic discipline, but by something harder to name, a quality of attention, a willingness to care deeply about something that will not reward you with immediate results, that demands patience measured not in days or weeks but in years and decades, that asks you to invest yourself fully in a project whose most important moments may happen long after you are gone. You find this quality in the engineers who designed the original spacecraft in the late 1960s and early 1970s, people who sat down with slide rules and early computers and worked out how to build something that would still be functioning 50 years later, in an environment no instrument had ever visited, under conditions they could only partially predict. They built in redundancy, they designed for longevity, they made choices that their successors, decades later, would quietly thank them for, including the decision to keep the RTGs running even when instruments were not actively using the power, maintaining the thermal environment aboard the spacecraft and buying time that nobody at launch could have known would one day be needed. You find it in the navigators who calculated the gravity assist trajectories, the ingenious route planning that used the gravitational pull of each planet to accelerate the spacecraft toward the next, like a cosmic game of billiards played across hundreds of millions of kilometers, with no margin for error and no second chances. The mathematics of those trajectories was extraordinarily complex, and it had to be right the first time. There was no practice run, there was no backup launch window. The planetary alignment that made the Grand Tour possible would not recur for another 175 years, and if the calculations were wrong, the opportunity would simply be gone. It was not wrong. It was precisely, beautifully, miraculously right. You find that same quality of attention in the people who work on the mission today. The engineers who spent months in 2023 and 2024 diagnosing and repairing a corrupted memory chip from across the solar system. The scientists who sit with magnetometer data and plasma wave readings and tease out the structure of an environment that has never been directly measured before. The mission planners who are making decisions right now about how to allocate the last remaining power, choosing which scientific legacy the mission will leave as its final gift to human knowledge. Many of these people could be doing other things. There is no shortage of exciting, well-funded, high-profile scientific and engineering work in the world. Artificial intelligence, genomics, quantum computing, climate science. The competition for talented minds is fierce, and the rewards on offer elsewhere are often considerably more tangible than the satisfaction of keeping a 50-year-old spacecraft alive on a power budget smaller than a nightlight. And yet they are here, working on Voyager, because something about this mission, its age, its distance, its history, the sheer audacity of what it has accomplished, draws a certain kind of person and holds them, not with financial incentives or career prestige, but with meaning, with the sense of being part of something larger than themselves, something that was here before them and will be remembered long after them. That is not nothing. In a world that often seems to reward the short-term and the spectacular over the patient and the profound, the Voyager mission is a quiet argument for a different set of values, for the idea that some things are worth doing slowly and carefully and with full commitment, even when the payoff is decades away, even when you will not be there to see the end. The influence of Voyager 1 on the scientists and engineers who came after it is difficult to overstate, not just in terms of specific technical knowledge, though that is considerable, but in terms of what it demonstrated was possible. Before Voyager, the outer solar system was largely terra incognita. Jupiter and Saturn had been observed through telescopes for centuries, but their moons were just points of light. Uranus and Neptune were blurry disks. Nobody had seen what those worlds actually looked like up close. Voyager 1 and 2 changed all of that. The images they sent back, the swirling clouds of Jupiter, the sculpted rings of Saturn, the volcanic hellscape of Io, the fractured ice shell of Europa, the hazy orange atmosphere of Titan, were not just scientifically valuable, they were revelatory. They showed the solar system as a collection of real, varied, complex, beautiful worlds. They turned abstract points of light into places. Europa, in particular, that smooth, ice-covered moon of Jupiter, crisscrossed with reddish-brown ridges, caught the scientific imagination in a way that has only intensified in the decades since. The Voyager images suggested that Europa's ice shell might be covering a liquid water ocean. Subsequent missions, particularly the Galileo spacecraft in the 1990s and 2000s, confirmed this strongly. Europa almost certainly has a vast ocean of liquid water beneath its frozen surface, kept liquid by the tidal heating generated by Jupiter's enormous gravitational pull. That ocean has been in contact with a rocky seafloor for billions of years. It may have hydrothermal vents. It may have the chemical energy sources that, on Earth, support entire ecosystems in the deepest, darkest parts of the ocean. The question of whether Europa's ocean harbors life is one of the most tantalizing in all of science, and the mission that is currently on its way to find out, NASA's Europa Clipper, launched in October 2024, exists in a direct line of scientific descent from Voyager 1. The images Voyager sent back in 1979 planted a seed. That seed grew through decades of analysis and debate and planning into one of the most ambitious planetary science missions ever launched. When Europa Clipper makes its close flybys of Europa and sends back detailed measurements of the ocean beneath the ice, it will be answering a question that Voyager 1 first made it possible to ask. That is legacy, not abstract, concrete and traceable and ongoing beyond Europa. The entire modern field of astrobiology, the scientific study of the potential for life beyond Earth, owes a significant debt to what Voyager revealed about the outer solar system. Before Voyager, the habitable zone around a star was conceived narrowly as the region where liquid water could exist on a planet's surface, warmed by stellar light. The assumption was that life required proximity to a star. Voyager's revelation of active geology on Io, the possibility of a subsurface ocean on Europa, and later Cassini's discovery of a water vapor plume erupting from Enceladus, another moon, this one orbiting Saturn, collectively dismantled that assumption. Liquid water, it turns out, can exist far from a star. Tidal heating, radioactive decay within a moon's rocky core, and other internal energy sources can maintain liquid water environments in the outer solar system and presumably around other stars as well. This dramatically expanded the potential real estate for life in the universe. The habitable zone is not a narrow ring around each star. It is potentially a vast three-dimensional volume, encompassing not just the surfaces of planets but the subsurface oceans of moons, the deep interiors of rocky bodies, environments that receive no direct starlight at all. This shift in thinking, from a narrow, sun-centered model of habitability to a broader, energy-centered one, is one of the most significant conceptual advances in the search for life beyond Earth, and Voyager 1's flyby of the Jovian system in 1979 is where it began. There is a generation of scientists alive today who were children when Voyager 1 launched, who grew up watching the images come back, who decided, in some cases explicitly because of those images, to pursue careers in planetary science or astrophysics or astrobiology, who have spent their professional lives building on what Voyager started, and now some of them are reaching the later stages of those careers, and they are watching Voyager 1 approach its final silence, and they are feeling something that does not have a simple name, grief certainly, but also gratitude, and a kind of awe at the scale of the journey they have been part of, not the spacecraft's journey, but their own. The journey of a scientific community that started with blurry telescope images of distant planets and has arrived, within a single human lifetime, at the threshold of searching for life in the ocean of an ice-covered moon. That is not a small arc. That is one of the great intellectual adventures in human history, and Voyager 1 is the spacecraft that started it, or rather, that gave it its first great leap forward. That turned the outer solar system from a set of theoretical objects into a set of real places worth caring about, worth studying, worth one day visiting with robotic emissaries, and perhaps, eventually, with something more. What about the next generation? The students sitting in classrooms right now, learning about space for the first time. The 10-year-old who asked why Pluto is not a planet anymore. The teenager who stayed up late watching a documentary about black holes and could not sleep afterward because the universe suddenly felt real in a way it had not before. The young engineer sketching spacecraft designs in a notebook during a class about something else entirely. Voyager 1 has something to say to all of them. Not in words, the spacecraft cannot speak, and when it goes silent it will carry no final message, no last transmission, no sign-off, but in what it represents, in what it proves. It proves that the gap between imagining something and building it can be crossed, that the distance between a concept in a physicist's mind and a machine in interstellar space is bridgeable by human effort, human ingenuity, and human persistence, that a 45-hour round-trip signal delay is not an insurmountable obstacle if you are patient and careful and refuse to give up, that a corrupted memory chip on a spacecraft 24 billion kilometers away is not a death sentence if you are smart enough and determined enough to find a way around it. It proves that some journeys are worth beginning even when you know you will not be there to see them end. The scientists who designed Voyager 1 are mostly gone now. The engineers who built it are largely retired or deceased. The mission controllers who guided it through its planetary flybys have handed off to successors who were not born when it launched. Nobody who set Voyager 1 on its course will be alive when it clears the Oort cloud. Nobody alive today will be alive when it makes its nearest approach to another star system 40,000 years from now. None of that stopped them. None of that stopped any of them at any stage of the mission, because the journey mattered more than whether any individual got to see the destination. The contribution mattered more than the credit. The knowledge mattered more than the convenience. There is a word in Japanese, mono no aware, that roughly translates as the bittersweet awareness of impermanence. The feeling you get when cherry blossoms fall, or when a piece of music ends, or when the light changes at the end of a summer afternoon, and you suddenly understand that this particular moment will never come again. It is not quite sadness, it is not quite joy, it is something richer than either, a recognition of beauty that is inseparable from its transience, a love that is deepened rather than diminished by the knowledge that it will not last. Voyager 1, in its final years, carries something of that quality. The signal is still arriving, the data is still flowing, the conversation is still happening for a little while longer. and because we know it is ending. Because the mathematics of radioactive decay and power budgets makes the end not just likely but certain. There is a quality of attention paid to it now that might not have been there if it were going to last forever. A tenderness, a wish to be present for the last of it, to listen carefully while there is still something to hear. That is not a bad way to relate to anything that will not last forever, which is to say, everything. Every measurement Voyager 1 has ever taken is archived. The data is preserved, studied, reanalyzed as new analytical techniques become available. Science published 30 years ago using Voyager data is still being cited in current research. The spacecraft's contributions to our understanding of Jupiter's magnetosphere, Saturn's ring dynamics, the structure of the heliosphere, the properties of the local interstellar medium. None of that goes away when the signal stops. It becomes part of the permanent foundation on which future science is built, and the golden record will keep drifting 1 billion years at minimum before it begins to degrade, carrying the sound of the wind and the surf, the music of Bach and Chuck Berry, and the Navajo night chant and the Bulgarian folk song, the greetings in 55 languages, the photograph of the traffic jam and the mother nursing her infant and the gymnast in mid-flight, moving through the dark between stars in the direction of a constellation called Ophiuchus at 17 kilometers per second for longer than the Earth has existed. Voyager 1 will outlast the signal, it will outlast the mission, it will outlast the civilization that built it and the star that powered it, and eventually, in the deepest possible future, perhaps even the matter it is made of. But right now, today, it is still here, still moving, still within earshot, barely, still sending home its faint whisper of data from the edge of the known. And there is one more thing to say about all of this. One final dimension to the story that we have been building toward across all these parts, all these hundreds of thousands of words, all these scales of space and time and human meaning. Something that brings the whole arc of Voyager 1's journey back, at last, to the question of what it means for you, personally, right now, reading or watching this, because this is not just a story about a spacecraft. It never was. Let us come all the way back. Back from the deep future and the dying stars and the faint hum of the interstellar medium and the golden record drifting through the dark. Back from the Oort cloud and the galactic year and the pale blue dot. Back to something immediate, something personal, something that lives not at the scale of billions of years but at the scale of a single human life. Your life. Right now, in this moment, you exist. That is, when you stop and really think about it, an almost incomprehensible fact. Not in a vague philosophical sense, but in a specific scientific traceable sense. The atoms that make up your body, the carbon in your cells, the iron in your blood, the calcium in your bones, the oxygen you are breathing right now, none of them were made on Earth. None of them were made in the sun. They were forged in the cores of stars that lived and died before our solar system existed. Stars that burned for millions or billions of years, fused lighter elements into heavier ones through nuclear fusion, and then died, some quietly, some catastrophically, scattering those elements across space. That scattered material drifted through the interstellar medium, the same interstellar medium that Voyager 1 is measuring right now. It moved through the same kinds of magnetic fields the magnetometer is recording. It was subject to the same plasma oscillations the plasma wave subsystem is detecting. Eventually, some of that material found its way into the cloud of gas and dust that collapsed 4.6 billion years ago to form our solar system, the sun, the planets, and everything on them, including you. You are, in the most literal and scientifically precise sense, made of stars. The iron in your blood was forged in the core of a massive star that exploded before our sun was born. The carbon that forms the backbone of every molecule in your DNA was assembled in the outer layers of a dying red giant billions of years ago. You are not separate from the cosmos. You are not a visitor looking at it from outside. You are part of it. You are the cosmos, in a very real sense, looking at itself. Voyager 1 is also made of stars. The aluminium and titanium and gold and copper and plutonium that make up the spacecraft were all forged in stellar interiors and supernova explosions before our solar system existed. Every component, every circuit, every gram of the golden record, all of it traces back to dead stars. And now that material is moving back out into the interstellar medium, back into the environment from which it came, carrying with it the imprint of the brief, extraordinary, improbable thing that happened to some of that stardust over the past 4.6 billion years. What happened is this: some of that stardust became alive, and some of what became alive became conscious, and some of what became conscious became curious enough to look up, to wonder, to ask questions, to build instruments, and launch them beyond the solar system. And in doing so, that stardust, through the medium of human hands and human minds, reached back into the environment it came from and began to measure it, began to understand it, began to know, in a way that no clump of matter has ever known before, something about the nature of the space between the stars. That is not a small story. That is one of the great stories, maybe the great story, the story of matter becoming aware of itself, of the universe developing the capacity to ask questions about its own nature. And Voyager 1 is one of the most vivid chapters in that story ever written. Now here is what I want you to take away from all of this, not just as information, but as something that lives in you after the video ends and you go back to whatever the rest of your day holds. The universe is vast, incomprehensibly, vertiginously, almost cruelly vast. The distances are real, the distance is real, the smallness of the pale blue dot is real. Nothing about the scale of the cosmos is exaggerated or metaphorical. If anything, every attempt to express it in human language falls short. The reality is more extreme than the words. And yet, here you are, on a planet that formed from the debris of ancient stars, orbiting a middle-aged star on the outer edge of an ordinary galaxy, in a universe 13.8 billion years old. And you are capable of knowing all of that. You are capable of launching something beyond the solar system. You are capable of fixing it from 24 billion kilometers away. You are capable of grieving when it goes silent and celebrating when it speaks again. You are capable of asking what it means and caring about the answer and making a video about it and watching a video about it and being moved by a spacecraft that has never met you and never will. That capacity for knowledge, for wonder, for connection across distance and time is not incidental to the universe. It is one of the most remarkable things the universe has produced, and it did not have to happen. The laws of physics did not require that stardust become curious. There is no equation that demands consciousness. There is no theorem that predicts wonder, and yet here it is. Here you are. Voyager 1 is moving away from us at 17 kilometers per second. Every day that passes, it is roughly 1.5 million kilometers farther from home. By the time you finish watching this video, it will have moved several thousand kilometers from where it was when you started. It does not know this. It does not know anything. It is a machine. It does not experience the journey. It does not feel the cold. It does not register the distances. It simply moves faithfully because the physics that governs the universe says that an object in motion stays in motion and there is nothing out there to slow it down. But we know. We are the part of this story that knows. We are the thing that launched it and tracked it and repaired it and listened to it and thought about what it means. We are the consciousness that the cosmos grew, somehow, over billions of years of stellar evolution and planetary formation and biological complexity and cultural development. And that consciousness Fragile, brief, improbable, extraordinary is what makes the whole journey meaningful. Carl Sagan said something once that has stayed with me, and that feels like exactly the right note on which to approach the end of this story. He said that we are a way for the cosmos to know itself, not poetically, not as a figure of speech, literally. The universe was here for 9 billion years before our solar system formed. It was here for another 4.5 billion years before human beings evolved. For most of its existence, it was unknowing. The stars burned and died, the galaxies collided and merged, the supernovae scattered their elements across space, and none of it was observed, none of it was understood, none of it was felt. It simply happened in the dark without witness. And then, on a small rocky planet orbiting an ordinary star, something changed. Chemistry became biology. Biology became consciousness. Consciousness became curiosity. And the universe, through the medium of living minds, began to know itself, began to understand its own history, its own structure, its own scale, began to ask where it came from and how it works and whether it is alone. Voyager 1 is one of the instruments through which that self-knowledge has been extended. Through it, we have learned something genuinely new about the environment beyond our solar system. We have confirmed the existence of the heliopause. We have measured the density and magnetic field of the local interstellar medium. We have detected the faint hum of plasma oscillations in the space between stars. We have carried a record of our music and our voices to a distance no human will ever personally travel, and in doing all of that, we have added, fractionally but really, to the universe's understanding of itself. So what do you do with all of this? How do you carry a story this large back into an ordinary day? I think you carry it lightly, not as a burden, but as a kind of perspective, a lens through which the ordinary becomes a little more extraordinary when you choose to look at it that way. The sky above you is not a backdrop. It is a window into the same interstellar medium that Voyager 1 is crossing right now. The air you are breathing is made of atoms with a history billions of years long. The fact that you can read or watch or think about any of this is the product of an improbable sequence of events stretching back to the formation of the universe itself. You are not a small thing in a large universe. You are the universe at this particular location, doing the remarkable thing of being aware of its own size. And that, right there, is the thing that no spacecraft, however far it travels, can replicate. The golden record can carry our music. It cannot carry this feeling, the feeling of being alive and small and connected and full of questions and unwilling to stop asking them. That feeling is yours. It is one of the most distinctively human things there is, and Voyager 1, that small golden, dying spacecraft moving through the dark between the stars, is perhaps the purest expression of it our species has ever managed to build. In a few years, the signal will stop. The conversation that began in 1977 will end. A team of dedicated people in a building in Pasadena will receive a last packet of data, log it, and know that there will not be a next one. The deep space network antennas will listen for a while longer, just to be sure, and then they will turn to other things. And Voyager 1 will continue its journey in silence, through the Oort cloud, through the interstellar medium, past distant stars on timescales measured in tens of thousands of years, into a future so remote that everything we know will be unrecognizably transformed. The golden record will drift, the music will drift, the sound of the wind and the surf and the mother's voice will drift, encoded in gold, through the dark between galaxies, for longer than the Earth has existed. And somewhere in that incomprehensible span of time, perhaps something will find it. Perhaps nothing will. Either way, the act of sending it was real. The love that went into choosing what to put on it was real. The tears of the engineers who kept it alive were real. The wonder that made it possible to imagine sending it in the first place was real. All of that is real. All of that matters. All of that is part of what it means to be alive on this pale blue dot, at this moment in the universe's long story, with eyes that can see the stars and minds that can wonder about them, and hands that can build something and launch it outward into the dark. We are here. We are curious. We are reaching, and somewhere out there, roughly 25 billion kilometers away, moving farther every second, so is Voyager 1. There is a version of the Voyager story that nobody tells often enough. Not the version about the spacecraft, about the instruments and the trajectory calculations and the golden record and the heliopause. The other version, the one about the people who never left. The scientists and engineers and mathematicians who gave years, sometimes entire careers, to a mission that required them to stay rooted to a desk in California, while the thing they built moved farther and farther away from everything they knew. Think about what that actually means. You spend years of your life on something. You pour your intelligence and your creativity and your professional reputation into designing and building and testing a machine. You watch it launch. You track it as it climbs away from Earth, crosses the inner solar system, reaches Jupiter, reaches Saturn, crosses the termination shock, crosses the heliopause, and you never go with it. You never will. The closest you will ever get to interstellar space is the data arriving on your screen 22 hours after it left a transmitter 25 billion kilometers away. There is something quietly heroic about that. Something that does not get celebrated nearly as loudly as the spacecraft itself, but that is just as essential to what the mission represents. The willingness to be the one who stays, to tend the connection rather than make the journey, to be the ear rather than the voice. In the history of exploration, this role, the one who stays home and maintains the thread back, has always been essential and almost always been under-acknowledged. The sailors who crossed oceans got the stories. The people who built the ships charted the routes, maintained the ports, tracked the vessels, and waited for their return. They were the infrastructure of exploration. Without them, the voyages would have ended badly or not begun at all. At JPL, the people who have tended the Voyager mission over 50 years are the modern version of those harbor masters and cartographers, and some of them have been doing it for a very long time indeed. Consider what it means to work on a mission that has been running longer than your entire life. Several members of the current Voyager team were born after the spacecraft launched. They grew up in a world where Voyager 1 was already a piece of history, already something they read about in school, already beyond the planets, already a symbol of human achievement. And then they went to university, studied physics or engineering or computer science, applied for jobs at JPL, and found themselves sitting down at a console to help manage a spacecraft that launched before their parents finished high school. There is something extraordinary about that continuity. The knowledge required to operate Voyager 1 is not the kind of thing you can fully learn from a manual. The spacecraft's systems are so old, so unique, and have behaved in so many unexpected ways over 50 years that a significant portion of the operational knowledge exists only in the minds of people who have worked with those systems long enough to develop an intuitive feel for them. The way a particular subsystem responds under certain thermal conditions, the subtle patterns in the telemetry that indicate a developing problem before it becomes a crisis. The history of every anomaly and every workaround and every improvised solution that has accumulated over 5 decades of continuous operation, that knowledge has to be passed on deliberately, carefully, person to person, the way a craft tradition is transmitted. And the Voyager team has been doing exactly that, mentoring younger engineers, documenting institutional memory, ensuring that when the people who have spent the longest time with the mission eventually move on, the understanding they carry does not disappear with them. This is, itself, a form of the Golden Record project. a human golden record, not stored on a gold-plated disc but encoded in the minds of a chain of people, passing it forward, ensuring continuity across time. There is a researcher named Ed Stone who served as the Voyager project scientist from the mission's beginning in 1972 all the way through to 2022, 50 years. 50 years as the scientific lead on a single mission. That is an almost unimaginable span of professional dedication. He was there for the Jupiter flybys, the Saturn flybys, the Uranus and Neptune flybys of Voyager 2, the crossing of the termination shock, the heliopause crossing. He was there for the memory chip crisis and the repair. He watched the mission go from a daring proposal to a functioning spacecraft to a piece of living history, and he stayed with it through all of it. In interviews toward the end of his tenure, Stone spoke about what it felt like to have the mission as a constant backdrop to his entire professional life. He described a kind of ongoing conversation with the spacecraft in a sense, but really with the universe. Each new boundary crossed, each new measurement taken, each new surprise revealed by the data was another exchange in a dialogue that had been running for 5 decades. And each surprise, and there were many, was a reminder that the universe is more interesting than our models of it, that reality consistently exceeds expectation, that the correct response to new data is always curiosity rather than defensiveness. That attitude, the willingness to be surprised, to let the data change your mind, to hold your models lightly and your observations carefully, is the deepest scientific lesson the Voyager mission has to teach. Not any specific fact about the heliosphere or the interstellar medium, though those are genuinely important, but the meta-lesson about how to engage with the unknown, with humility, with patience, with the understanding that the universe does not owe you confirmation of your prior beliefs. Now let us talk about something that sits at the intersection of the scientific and the deeply human, something that the Voyager mission raises in a way few other scientific endeavors do. When we send something to a place we cannot go, when we build a proxy, an emissary, a machine to experience what we cannot experience ourselves, what exactly are we doing? What is the relationship between us and the thing we built? Is Voyager 1 an extension of us in some meaningful sense? Or is it entirely separate, a tool, nothing more, that we happen to have launched into an interesting location? I think the answer is somewhere more complex and more interesting than either extreme. Voyager 1 is not conscious. It does not experience anything. It does not know it is in interstellar space. It does not feel the cold or register the distance or have any awareness of the golden record on its hull. In that sense, it is entirely separate from us, a machine executing its programming, transmitting its sensor readings, moving according to the laws of physics, but it was made by us. Every decision about what to put on it, how to build it, what to measure, where to aim it, those decisions were made by human minds, shaped by human curiosity, driven by human values. The golden record was chosen by human beings who cared about representing the full texture of human life. The instruments were designed by scientists who wanted to answer specific questions about the universe. The trajectory was calculated by navigators who wanted to use every available gravitational assist to send it as far as possible. Voyager 1 is, in a very real sense, the physical expression of a set of human intentions and human values, and in that sense, it is very much a part of us, an extension of us, a piece of human consciousness crystallized into metal and code and gold, sent out into the universe to do what consciousness does: observe, measure, ask questions, reach toward the unknown. When Voyager 1 crosses the heliopause and enters interstellar space, it is not just a machine crossing a boundary, it is humanity crossing a boundary. It is the first time that the intentions and curiosity of a thinking species have physically extended beyond the home star system. That is not metaphor. That is as real and as significant as any other threshold in the history of exploration. Here is a question that might seem strange, but that I think is worth asking seriously. What do we owe Voyager 1? Not in a legal sense, not in a financial sense, in a moral sense perhaps, or at least in a cultural one. What does it mean to have built something that has served so faithfully for so long at such extraordinary distances, and to be approaching the point of losing contact with it forever? Some people find the idea of owing anything to a machine category error, a confusion between living things, which can suffer and therefore have interests, and inanimate objects which cannot. And in a strict philosophical sense, they are right. Voyager 1 cannot suffer. It does not have interests. It cannot be wronged. But there is another sense in which what we owe Voyager 1 is really what we owe to ourselves, to the version of ourselves that built it, to the values it embodies: curiosity, reach, the willingness to send something into the unknown without guarantee of return. What we owe is attention, presence, the willingness to mark its ending as the significant event it is, rather than letting it slip by as just another item in the news feed. When the signal goes quiet for the last time, it deserves to be felt, not just logged and moved on from. Felt, the way the end of anything genuinely important deserves to be felt, with full awareness of what it was, what it meant, what it cost, and what it gave. That is not sentimentality. That is the appropriate human response to something extraordinary coming to an end. There is a word in Welsh, hiliaeth, that has no direct translation in English. It refers to a kind of longing, a homesickness for something you cannot return to, a grief for something lost that is mixed with love and the bittersweet awareness that the thing you are grieving for was beautiful, precisely because it was finite. It is the feeling you get when you look at an old photograph and feel the weight of all the time that has passed since it was taken, when you hear a piece of music from your childhood and feel simultaneously the joy of the memory and the ache of its distance. Voyager 1, as it approaches its final silence, carries something of hiliaeth with it, or rather, it provokes it in us. We cannot go back to 1977. We cannot relive the Jupiter flyby or the first image of Io's volcanoes or the moment the heliopause crossing was confirmed. We cannot recover the years of data already received or the people who gave their working lives to receiving it. It is all in the past, receding like the spacecraft itself, growing more distant with every passing second. But we can do what humans have always done with hiliaeth. We can hold it, we can honor it, we can let it remind us of what mattered, and use that reminder to pay better attention to what is still here, still happening, still transmitting. Voyager 1 is still here, still transmitting, still sending home its faint, extraordinary signal from the edge of the known. And as long as that is true, the appropriate response is not grief but attention, not mourning but wonder. So here is what I want to leave you with. As we continue this journey together through the full story of the most distant object humanity has ever made, you live in a remarkable moment. Not just in the sense that every moment is remarkable, though every moment is, but in a specific, historically contingent sense. You are alive during the final active years of the first interstellar mission in the history of life on Earth. You will likely be alive when the last signal arrives. You will have the chance to mark that moment consciously, to understand what it means, to feel its weight appropriately. Most of the significant moments in the history of exploration happened before anyone alive today was born. Nobody currently living watched Columbus's ships disappear over the western horizon. Nobody watched Magellan's crew complete the first circumnavigation of the globe. Nobody was there when the first human footprint was pressed into the lunar dust. Those moments belong to history now, preserved in documents and photographs and recordings, always slightly beyond our direct experience. But this one, the end of Voyager 1's active mission, is ours. It is happening now. It belongs to the people who are alive to witness it, and witnessing it consciously, with full understanding of what it represents, is a privilege that will not be repeated. The universe gives us very few moments like this, moments when the scale of cosmic time and the scale of human time briefly coincide, when something as vast as interstellar space and something as intimate as a small team of engineers at a console in California are part of the same story at the same moment for you to observe and feel and remember. Do not waste it. Look up. Pay attention. Stay curious. The signal is still arriving, and if this journey left you staring at the dark between the stars, click the video on your screen right now. In this video, we explore why interstellar travel gets more terrifying the further you go. Find out why the universe does not get more welcoming the deeper you go into it. Trust me, you need to see this one. See you there.